Hi, I'm Starkey, and this is my lab for presentation. So to introduce this lab, the purpose of it was to predict the motion of a spring mass system. Our specific one had a mass in the middle and two springs on either side. With the use of the physics principles we have learned, and we must demonstrate this motion to a point where we can predict it. The fundamental principles that we'll be using is Newton's second law and the energy principle. Our system is the mass brings in Earth, so therefore our springs are none. And with this, we know that our change in energy can be zero, which will be useful for the calculations. In our results, we will be able to predict the motion of the system. So the physics equation we'll be using is whenever you have to use the energy principle equation, which we know that the kinetic, gravitational potential, and the spring potential are all going to equal zero because we define the entire thing as our system. And our spring potential is going to be zero point 0.5 times r ks, which is the spring constant, times s, which is the distance the spring moves, squared. We also have kinetic energy, which is 1/2 mv squared, as well as our potential, mg the delta h. And obviously we have our obvious stuff like force of gravity equals negative mg y hat. And we can also use our position updates and our velocity updates to find how much it moves when we find our velocities as such using our energy equation. So that's basically what we're going to do. We're going to use our energy equation for different points to find our velocities and all that and the changes. So therefore we can calculate what's going to happen. We'll also use the oscillation formula later on in the lab. So in the experiment, the initial conditions are our time is 0 seconds, velocity 0 seconds, initial position is that those meters, and we have our constants such as gravity, mass, our k value, and our initial length all given to us by pre-lecture video 52, which we can assume is consistent with our springs. If we see in the bottom left video, we can see how this mass moves around and how positions change due to these two springs on either side. Now we can look at the code. And if we look at the code, we can see in our initials we have to find our L, which is just going to be our ball position minus our spring position. We can find that by dividing by magnitude, and then we can get our change in S. And we can also use plug in our energy equations to the code by just stating what kinetic, U gravity, and US is going to equal, which will make our energy equation work. And then we also had to calculate the gravitational force, spring force, and our net force, which is all basic calculations that we've been doing forever. F spring, just negative KS, talked about that. And then by applying the momentum principles, and then we can update the spring to show us our new changes, and therefore give us more. And then while we calculate energy changes, and by doing all this, basically what we're doing is finding these new positions and these new velocities that people is going to reach. Now, the results of this lab, we can see the change in energy versus time. We can see our delta, so meaning our total energy is zero throughout the whole thing, which is perfect. That's what we're looking for. And we can see how our kinetic energy and our potentials all always cancel out during the oscillations, showing how our potential or our total energy is zero. You can also see in our x-axis and times, they are both really similar graphs as they look the same, which shows our experiment did work in comparison with the model because they're very similar, which means we reach the theoretical point of our lab, and we can say that there is background to the results we got in showing how our energy equals zero. It's possible, of course, that cases of error, though, if tracker isn't 100%, you have to manually click the points on your point mass system. So the positions of it might be slightly off, changing your calculations a little bit. Also, there is technically a chance for screen deformation in your video, which would not be accounted for in the model, along with air resistance that the mass would have to encounter when it's swinging from side and up and down. Now, for the first reasoning question, if is the energy principle satisfied? Well, we can see that the energy principle is satisfied because, as stated, our total energy has to equal zero if they all cancel out because we put everything as our system. And we can see in our graph that our change in energy versus time, our delta E, meaning our total energy change, is zero. We can take for what does it mean to, we're trying to figure out the oscillations by using the x and y. And to do this, you can take the approximate time it took in the x and y direction to reach the same coordinate, the same place, aka oscillation. So in the graph, you, we would subtract out the times, and we got 1.7 seconds and 1.52 seconds for the line x oscillation. Now, these are obviously both going to be slightly different because